Hello, and thank you for clicking on the video PowerPoints in the Modern Welding textbook, Chapter 13, Oxy-Fuel Welding. This chapter is a very large chapter, a lot of information. We're going to try to break it down individually, slide by slide. Hopefully this will help you supplement your learning after reading the chapter. Hopefully we'll be able to tie up any loose ends that you have, any questions you may have. So let's get started. All right, Chapter 13, Oxy-Fuel Gas Welding. Our learning objectives are demonstrate the safe storage, handling, and movement of oxygen, acetylene, and other fuel gas cylinders. Explain how to assemble an oxyacetylene welding outfit. Demonstrate the correct method for testing for leaks on all components of the oxyacetylene welding outfit. If you look at this picture, this is what a typical oxyacetylene outfit looks like. We have our cylinder cart where we have both cylinders chained up in a vertical standing position. Each cylinder has a regulator connected to it, hoses connected to the regulator, and there we see our oxyacetylene torch. Demonstrate the correct method of turning on, lighting, and shutting down an oxyacetylene welding outfit. We'll do that in this chapter with the PowerPoints and the reading. But when we get into the shop, obviously that's really where we're going to learn how to turn on all the equipment and shut it down. Ours is going to be a little bit different. We're not going to have an oxy-fuel outfit, only one in our shop. We're going to obviously run off a manifold system, so our routine is going to be a little bit different than the one in the book in the PowerPoints. But 9 times, I'd say maybe 8 times out of 10, when you're out in the field or at a job, you're going to have a regular outfit with just the cylinders and the cylinder cart. Select the correct tip size, working pressures, and welding procedure to use for welding various thicknesses of mild steel in various positions. Adjust an oxyacetylene welding torch to produce a neutral flame and to be able to identify other types of welding flames. Run a continuous weld pull on a base metal using an oxyacetylene welding torch, and make quality welds in butt joints, lap joints, outside corner joints, inside corner joints, and T-joints. Hopefully by the end of the semester, we'll be able to weld on T-joints, but the big ones that we're going to be welding on, obviously we're going to start out with butt joints, outside corner joints, inside corner joints, some lap joints. That's more what we're going to do for brazing. And then, like I said, T-joints are difficult weld to make, but hopefully by the end of the semester, we'll be able to weld on T-joints. Make quality welds in butt joints in a flat, vertical, horizontal, and overhead position. Make quality welds in butt joints in the flat, vertical, horizontal positions, overhead positions. Make quality welds in butt joints in the flat, vertical, horizontal, and overhead positions. We're really going to stick to the flat position in most of our welds. Obviously, if you learn it, you pick it up quick, the skill quick, you can move on and try the other different positions, but really we're going to work in the flat and horizontal positions for this course. Recognize good and defective welds. Pass a test on safe practices and procedures to follow for oxy-fuel gas welding. Oxy-fuel gas welding widely is used to repair work, fabricating small projects, and cutting. Fundamentals include basic skills important to other forms of welding. Beginners can easily observe the fusion process during oxy-fuel gas welding. Oxy-fuel gas welding joins pieces of metal by heating them with a gas flame to the melting point, and then molten portions fuse together. Basically, what we're going to do is we're going to take 2 pieces of base metal and fuse them together to make 1 piece. I mean, that's basically what welding is. You're taking 2 pieces and making them 1. We're going to do that with a flame instead of an arc in this course. Oxy-fuel gas welding process. The oxy-fuel gas flame is produced by burning fuel gas in the presence of oxygen. This process provides a clean flame that produces the heat needed for welding. We take a look at our torch here on the side. We have our oxygen with our green hose and our fuel, which would be acetylene, with our red hose. They mix together in the mixing chamber. That gas flows out the end. Our welding tip, we take our striker, ignite that gas, and then we have our flame. Welding flames, a very intense concentrated flame is applied to the metal. The molten pool runs together and fuse. The edges of the two pieces become one. To obtain more heat, a torch tip with a larger orifice is used to produce a larger flame. The thickness of the metal that can be welded depends on the quantity of fuel gas burned per unit of time. This obtaining the heat in the torch tip, we talked a little bit about that in the last chapter. If you watched the video PowerPoints for chapter 12, the larger the hole, the larger the flame, the thicker the metal that you'll be able to weld on. We'll be using a 2-tip, so we will be welding on 1/8" steel. Welding flames, too much fuel gas results in a carburizing flame that adds unwanted carbon to the metal being welded. A neutral flame is desirable. Too much oxygen results in an oxidizing flame that burns the metal. If you look here in the picture, we have our bullet-shaped inner cone. That's what we're going to use to create our puddle or start to melt our two pieces of metal. That is a neutral flame. Welding flames, an oxyacetylene welding flame is the hottest oxy-fuel gas flame. It is hot enough to melt common metals. The melting point for most carbon steel is around 2,600 to 2,800 degrees Fahrenheit. Our torch flame is going to be anywhere from 63 to 6,500 degrees Fahrenheit. So we're almost 3 times the amount of heat needed to start melting the metal. So we want to make sure that we do have a neutral flame, not an oxidizing flame. An oxidizing flame, which in the last slide talked about, you have too much oxygen in your mix, will end up just burning through the metal, almost cutting it. A carburizing flame where you have too much acetylene to your mix, to your acetylene oxygen mix, won't be hot enough to start melting the metal. So we've got to get a 1-to-1 ratio, 1 part oxygen, 1 part gas or acetylene to make that neutral flame. If you look here, after we've dialed in our flame with our needle valves on our torch, a neutral flame is this nice bright white cone, bullet-shaped cone, and then it has this blue tail to it with just little to none or no flames at the end. When we first light the torch, we're going to get an actual flame like you would see on a lighter, and then as we steadily add in oxygen, that's when this flame is going to come down and start to get this blue look, and the oxygen is what's going to heat our flame and give it all that nice heat to melt our base metal. Oxy-fuel gas welding outfit. The oxy-fuel gas welding outfit consists of the oxygen and fuel gas cylinders, the regulators, the hoses, the hose fittings for each gas, a welding torch, and the most common type of oxy-fuel gas welding torch is a positive pressure torch. If you remember the slide or go back to the slide in the beginning, or actually, assembling the welding outfit, securely fasten oxygen and fuel gas cylinders in the vertical position. We always want to make sure they're chained up. Clean the oxygen and fuel gas cylinder outlets by cracking the valve. I talked about this a little bit in the last chapter. If you look here at the cylinder valve, this is the fitting that our regulator is going to go on. We want to make sure there's no debris in that fitting. So we want to make sure that that is away from our face and our body, and we just want to crack the top of the cylinder, forcing the gas out or oxygen, and it'll force any debris that's kind of laying in there through, before we put the regulator on. We don't want to have the regulator put that on, and then when we turn the cylinder on, have that debris go through the regulator or the hose. Could do damage, could clog it up. So we just want to make sure that that's clean before we attach the regulator. Attach the fuel gas hose to the fuel gas regulator. Obviously, we want to make sure that we have our flash arresters on there with a check valve. We want to attach our oxygen hoses and to our regulators next, tighten the nuts with the proper wrench, and attach a flashback arrestor between the regulator and hose. Purge hoses before attaching. Attach the torch to the hoses. Torch inlet fittings have a right-handed thread and left-handed threads to match the regulators and hoses. Select the proper size torch tip and place it into the torch and torch tube, tightening it securely. Purging your hoses is just, again, we want to make sure that we run gas or oxygen through the hoses and it comes out the end before we hook up our torch to them. And there's no debris in the hoses and everything's nice and the lines are clear. Safety wise, before opening a cylinder valves to purge the hoses, make sure you are standing to the side of the regulator gauges. We want to make sure all that pressure when we open up that cylinder valve that we're not in the line of the gauges in case there's some defect in the regulator that we have causes an explosion or a blowout of the regulator. So again, when we open that pressure, that cylinder valve, and all that pressure comes out of the gas, we kind of want to stand to the side so that we're not in the line of fire. Checking for gas leaks, turn the regulator screws out all the way, open the cylinder valves, and slowly build up pressure in the regulators. Put a soap and water soap sud solution on the outside of joints suspected of leaking, just like you check for a flat tire or a hole in your tire. You want to put some soap suds on there. Once you see bubbles, that's when you know the leak is occurring. Safety slide, never use a flame or oil or any kind of any kind to test for leaks. We talked about that in chapter 12, or I talked about a little bit already. Do not use the system until the leaking joints are repaired. Obviously, just like you don't want to drive on a tire that has a leak, we don't want to use any kind of acetylene torch when there's leaking gas. After parts are replaced or repaired, perform another leak test before lighting the torch. Checking regulators. A leaking regulator valve allows pressure to rise uncomfortably inside the regulator. Check regulators for leaks immediately after setting the working pressure. With our manifold system, since it's cut off like line by line by line as it's plumbed in to the building, if you're at the beginning of the line, when you set your working pressure and then open your needle valve, you'll sometimes see your gauge drop in pressure because of the manifold system. You're pulling off each line. So you always want to set your working pressure, check it with your needle valve, watch, because it's going to have some drop to it, especially if you're all the way at the end, the last station on the line, your drop's going to be a little bit more drastic. So that's one thing we'll go over when we get into the shop. Make sure that you understand it, but just giving you a heads up. Selecting a torch tip. Selection of the correct torch tip depends on the thickness of the base metal. The tip size is determined by the size of the hole or orifice. The orifice size determines the amount of fuel gas and oxygen fed to the flame. If the torch tip orifice is too small, not enough heat will be available to melt the metal. If the torch tip is too large, poor welds will result. You'll just end up burning the metal and you won't actually fuse it together. Your welds will be convex looking, weak welds, and probably in most situations, you'll end up just burning holes in your base metals. Turning on the oxyacetylene outfit, the procedure for that: visually check components of the outfit for damage and ensure that the cylinder valves are closed. Ensure the regulators are closed before opening cylinder valves. Stand to one side as you open the cylinder valves. Slowly turn on the oxygen cylinder valve clockwise until it is fully open. Cylinder pressure can be 220 psi. A rapid flow of high pressure gas could rupture the regulator, diaphragm, or gauges. Turning on the oxyacetylene outfit, the procedure continued. Step 5, turn the acetylene torch valve 1/2 turn clockwise. set the correct working pressure on the acetylene regulator gauge, close the acetylene torch valve, open the oxygen torch valve, open half to one, turn counterclockwise. And finally, step 9, turn the oxygen regulator adjusting screw clockwise until the desired working pressure is obtained. And number 10, close the oxygen torch valve. So for our procedure, again, it's going to be a lot easier to do this in the shop, but I'll kind of just give you a brief description of how we'll do it. There'll be 2 ball valves coming down off the manifold system, one for oxygen, one for acetylene. They'll be plumbed into our regulators, and our hose is connected to our regulators, which is connected to our torch. What I do is I open each ball valve so the gas is now in each regulator. I adjust the adjusting screw on the regulators to my desired PSI, which in our case will be 3 PSI for acetylene, 3 PSI for oxygen. Once that's set, I open my needle valves to check to see how much drift I have on my regulator. If I'm at 3 PSI and it drifts down to 2, I shut my needle valve back off. I know that it's going to drop 1 PSI. So I open my needle valve back up. It drops to 2. I tighten my adjusting screw so it raises the pressure to 3, shut my needle valve off. The book says to just open your needle valve and adjust your screw. You can do that once you're experienced, but until you get used to lighting or regulating, using the regulators and adjusting them to your desired PSI, I don't want you to stand there with your needle valve open and have acetylene gas just pouring out through the shop. You're going to be within a couple of feet of one another throughout your workstation. So I don't want this guy lighting his torch over here and this girl having her acetylene wide open, trying to adjust her desired PSI level. So until you get used to it, kind of make sure you're shutting off your needle valves as you go. Lighting and adjusting the welding torch flame. The procedure for it is open the acetylene torch valve about a 1/16 turn, light the acetylene at the torch tip using a striker, open the acetylene torch valve until the flame becomes turbulent at about 3/4 of an inch to an inch from the end of the tip. Another good way to do that is, I usually go quarter turn with my acetylene needle valve, light the torch, and I start adding acetylene until the black smoke is gone. You have a nice feathered flame, and then I start adding my oxygen. If you go like a half turn or like a full turn with your acetylene before you light it, you're gonna have like a flamethrower coming out. So I'd rather you go a little bit less with the acetylene and not have like this huge flame coming out of the end of your torch. If you don't go a quarter turn, if you just turn it, just crack it open and light it, you're going to have black smoke and debris or kind of like ashy smoke throughout the shop. We don't want that either. So you don't want to go too less and you don't want to go too much. That's why I would say quarter turn to maybe half turn with your acetylene before you light it. Step 4, after the acetylene is regulated, turn on the oxygen torch valve slowly and adjust it to attain a neutral flame. This, for students that are first trying it, is kind of complicated because the needle valves are a little bit touchy on some of the torches. So if you crack it open with the oxygen, it's going to be too much oxygen right away. It'll put out your flame. You probably will have a backfire because first, when we talked about backfire in the last chapter, if you have an obstruction or a stopping of the flow of gas at any time, you're going to have like a popping or it's just going to go out. So we want to kind of ease that oxygen in and then dial it down. You'll see your flame come from feathered flame, like your normal lighter, and then it'll start to get blue as you add more and more oxygen, and then it'll come down. The tail of your flame will come down till you have a neutral flame. Some of the fine adjustments of the acetylene and oxygen torch valves may be required. It's going to take you a minute to get used to finding a neutral flame, but once you have it in there, it's just like riding a bike. You'll be able to do it every time. The big thing is you've got to have a neutral flame to oxyacetylene weld. If you have an oxidizing flame or a carburizing flame, it won't work. It'll get very frustrating. So it is very key to pick up getting that neutral flame, keeping that neutral flame to do oxyacetylene welding. It's not like arc welding where you can run hot and still have a good weld, or run a little cold and still produce a pretty good weld. You got to have it dialed in for this to work. Everything has got to be dialed in. Turning off a torch and shutting down. If leaving the station for a few minutes, simply turn off the torch. First turn off the acetylene gas, next turn off the oxygen valve, needle valve. If the equipment will be idle for more than a few minutes, the outfit should be completely shut off. We'll shut it off completely at the end of the night. If you go out, need to go to the bathroom, need a break, something like that, yeah, just shutting it off with the torch will be fine. The other thing is too, like, my style contradicts the book style. And in welding, that's one of the beauties I like about welding is there's 100 ways to do welding and different processes of welding. As long as the result in the end is a positive one, a good one, you know, do it the way you're most comfortable with. I like to turn off the oxygen cylinder or the oxygen needle valve off first, and then acetylene, because sometimes if your oxygen is higher than your acetylene, you're going to get a pop for that too. So I'd rather turn off the oxygen needle valve first. That'll bring your acetylene down to just a regular flame like you would have with a lighter, and then turn it off. But either way works. So again, whichever is more comfortable for you. I don't want to sound like I'm just totally against the book. I was taught a different way. It works the same. So the outcome is a good one. So whichever, when we get in there, you know, try both ways, whichever is more comfortable for you, stick to it. Shutting down the outfit procedure. Turn on the flame, or turn the flame off, closing the acetylene torch valve, then close the oxygen torch valve. Completely close the acetylene cylinder valve, then close the oxygen cylinder valve. Reopen the oxygen and acetylene torch valves. Watch as the gauge decrease to 0. So basically, that last step, all you're doing is bleeding the line to make sure all the gas is out of everything. What we'll do with the manifold system is, just like we turned it on, we'll turn it off. We'll start with the ball valves coming down from the ceiling that are plumbed in from outside, turn those off. So now we have isolated the gas coming from outside to inside to that point. There's still gas in our regulators, in our hoses, in our torch. So next, we want to open up the adjusting screws to let that pressure out of the regulators. Then finally, open our needle valves, let everything bleed out of our regulator, our hoses, our torch, and we'll see the gauges, our working pressure gauges on the regulators go from 3 to 0. Now we shut back off our needle valves. We know that everything is bled, all the gas is out. Number 4 for the shutting down the outfit. If it was just the cylinders, step 4, turn the adjusting screws on both regulators clockwise until they fill loose. Close the torch valves and then hang the welding torch up and hose and ensure that the cylinders are safely secured. Torch adjustments. A torch can be adjusted to produce the following: neutral flame, carburizing flame, oxidizing flame. A disruption of gas flow at the tip causes a backfire. We've talked about that already. If the backfire is not stopped, a flashback can result. So if it pops and then it keeps popping, it can result in a flashback. Generally, when flashbacks occurs, a squealing or sharp hissing sound will be heard. Anytime we hear that, we got to stop what we're doing, shut off the needle valves. If it becomes, you become nervous and get excited and you just put the torch down, you forget about the needle valves, shut the ball valves off of the manifold system. We want to isolate the flow of gas, stop the flow of gas. So, you know, hopefully you don't get in a panic and you can just shut off your needle valves. But if you are in a panic and you're just standing there and you're froze, reach up and shut off the ball valves. We want to, again, isolate that flow of gas or stop the flow of gas. Safety slide, flashback is extremely dangerous occurrence. Action must be taken immediately to extinguish the flame. Hopefully we will not have to extinguish anything throughout the course. Like I said, as soon as we start hearing that popping, you know, you're gonna realize something's not right and we gotta shut off our gases, shut off our needle valves. Torch positions, movements, and angles. Travel angle, we talked about this stuff in chapter 3. The travel angle between the axis of the torch in line perpendicular to the weld axis. Our travel angle, if our torch is pointed from right to left and we're going from right to left, we're pushing our travel angle is a push travel angle because we're going in the same direction as our arc or our flame. If our flame is pointed right to left and we're traveling left to right, we are at a drag travel angle. Our work angle, the angle between a line perpendicular to the major workpiece and a plane determined by the center line of the torch weld. Basically what they're saying there is, if this is my piece of base metal and my torch has that 45, my welding tip has that 45-degree angle on it, I want to drop it another 45 degrees and kind of work across that piece of base metal. That work angle, that drop from this perpendicular up, that 45 degrees, is my work angle. Forehand welding and backhand welding. In oxy-fuel welding, we really don't have push travel angle. We have forehand welding, and we don't have drag travel angle. We have backhand welding. They mean the same things. You're going to hear in all throughout arc welding, push and drag travel angles. Forehand welding, moving the torch in the direction that the tip is pointed. Travel angle is also called push angle. Backhand welding, the torch tip is back toward the weld bead that was created. The travel angle is called a drag angle. Torch motions, the tip of the welding torch should be moved slightly as the weld progresses. A weaving, oscillating, or circular motion can be used. So obviously this would be our circle motion. This will be our Z-weave motion. This one here I've never done. This is more like a whipping motion, I would say, or a horizontal Z, and this would be another circular motion, but the circle is just going the opposite direction. Running a continuous weld pool, the size of the weld pool is in proportion to its depth. The pool surface appearance indicates the type of flame coming from the torch. A correctly adjusted flame prevents oxidizing to the surface of the pool, so that it doesn't have oxidizing would be it's burning it up, or it's melting too fast. It's not creating a good weld puddle, and your weld bead is going to be affected from it. The tip of the inner cone of the torch must be held within the boundary of the weld pool at all times. So your flame is going to be very, very close to your puddle. You're going to need that heat to be there the whole time, so we want to keep it pretty close. All this action is going to happen pretty close. I would say within, I won't want to get any further than like a 1/4 inch to 3/8 of an inch away from our weld pool. From the tip of our welding tip, our flame is going to probably be about a 1/4 inch to maybe 3/8, probably more like 1/4 inch. So then the distance from the end of that, the end of our cone of our neutral flame to our base metal is going to stay within a 1/4 inch too. Those circles, that welding motion that we were doing, that again, our weld bead is only going to be, I wouldn't make it any bigger than probably 3/8. So that circle isn't going to be huge, it's going to be tiny. Everything's going to work in small spaces. Running a continuous weld pool or puddle. If the weld puddle sinks or sags too far, lower the angle of the torch or increase the speed of the movement. The eye of the weld puddle indicates the movement of the molten metal. So if we're doing the circles, you know, we want to kind of keep them in. Like I said, everything's going to kind of work together. We're going to be in a tight area, tight working space. If our puddle starts to droop through, we're too hot, or if our flame needs adjusted, or we're too close to our base metal. If our puddle starts to get too wide and get out of control, we're going too slow and we need to kind of speed up. If our puddle starts to get too narrow and too thin, we're moving too fast. We're not taking enough time. So our bead can tell us a lot about our weld, whether we're moving too fast or too slow, if we're too hot or too cold. Welds made without welding rods. Welds that can be made without the use of a welding rod, overlapped square groove, flange butt joint. These are good weld exercises to begin with. We're going to start out running stringers on just a flat piece of base metal. We're going to start out our first day welding with just running stringers, which are on a flat piece of base metal with no filler rod, just getting used to the torch, getting used to creating a neutral flame, creating a puddle, and then manipulating that puddle or carrying it across the entire way of the base metal. It's a great exercise to begin with. And then once we kind of master that, then we'll add the filler metal in the same exercise. Before we start welding joints, we want to kind of run stringers on just a flat piece of metal to get used to creating the puddle, manipulating the puddle, running a straight bead, and then adding the filler metal. Welds made with a welding rod. To become proficient in gas welding, certain exercises must be planned and practiced. The basic weld joints are butt weld, lap weld, corner, outside and inside, T-joint and edge. Like I said, once we get done running stringers, our first weld will be butt joint. Then we'll go to outside corner and inside corner. And then we'll start doing the fillet welds with either a lap or a T. We'll start out with groove welds, butt and corner, and then move to the fillet welds. The basic weld positions: flat position, horizontal, vertical, and overhead. We went over these in chapter 3. 1 would be flat, 2 horizontal, 3 vertical, 4 overhead. With this course, we're going to just try and do flat and horizontal. If you can pick those up and you want to progress vertical and overhead, this is an older style of welding. It's not done a whole lot anymore, oxyacetylene fuel welding, but it is a good way to lay a base or foundation for your welding career. It teaches us how to create a puddle, to see what a puddle looks like, how to manipulate that puddle, how to create a weld bead, how to fill a joint, all the basics that you're going to use with MIG, TIG, stick are grounded out of oxyacetylene welding. Welding rod and running a bead. To obtain a strong weld, metal from a weld rod is fed into the weld pool. This decreases its depth and increases the thickness of the metal in the weld area. The bead in a correctly made groove weld should be slightly convex, so it's going to have that round look to it, a round contour. Fillet welds can be made either convex or concave. That's why we're going to kind of wait to do the fillet welds. They're a little bit tougher. You got to constantly add filler metal to get that contour to it. It's a tougher weld to make with oxyacetylene. All right, weld with filler rod in a flat position, butt joint. So if we take a look, remember how I told you this 45-degree angle, we're going to need to kind of not only create our puddle, get our heat, but then it'll actually preheat the base metals as we move along, making it a little easier to weld. The welding rod is going to be at about a 45 too, but you can drop it down When I weld with filler rod, oxyacetylene, I'm probably about like 20 degree, I would say maybe 25 degrees. The only problem with that you got to watch is if you lay this down, that heat's not only going to just heat the base metal, but it's going to start heating this welding rod. So the higher you have your angle here, the less heat is going to come up this rod. That's why when we were talking about PPE and gloves, I said that most welders, for their filler rod hand, they use a heavier glove because that heat is going to also be coming up this rod and making it pretty hot. So just remember, it might be a little easier to melt the filler rod if you have a lower angle, but if you have a higher angle, it's going to be less heat on your hand itself. So yeah, this is our final, like that convex look, that round contour that I was talking about, and then also getting that weld look on the bottom side of our root opening. To start out with, we'll just use butt joints that are butted together. We won't use a root opening. As we progress on and on through the course, then we'll start making open root welds. Welding rod and running a bead, the weld pull condition and the melting rate of the rod can be adjusted with small changes to the torch position. As the welding rod melts, it becomes necessary to reposition your grip on the welding rod. A lot of times, like fingering it full. As the welding rod melts, it becomes necessary to reposition the grip of the welding rod. A lot of times our welding rod is 3 foot long, so we cut it in half, so it's about 1.5 feet. A lot of times welders, they'll go all the way almost to the end of the welding rod, so they don't have to kind of inchworm it down once they start feeding it into the weld. It's just, one of those things that you're going to have to adjust to the way it's most comfortable for you. However, you can feed it in pretty easily, then you can kind of keep it wherever. If you have trouble, you're going to want a lot of filler rod to start. That way you can kind of make it through your whole joint, make one complete pass without having to adjust your fingers. Using different size welding rods for the same weld can cause problems. The big thing with that is, take your snips, your whelpers, after you're done making a weld, and kind of just cut your filler rod so that you have it's not necessarily, you don't have to get a new piece every time, but it's a fresh start on that filler rod itself. A good weld is achieved by coordinating handling of the welding torch and the welding rod. Yes, you're going to have to start, once we get going here, you're going to have to work in concert with each of your hands. This is, the big thing with oxyacetylene, like I had just talked about, it is a building block, a foundation for welding and all the processes. It's also the practice that will give you that you're going to need for TIG welding. It's going to be basically the same style. You're going to be using both hands, but in TIG also, if you're using the bigger machines, you'll have a foot pedal to control the arc. Like I said, it's just a really good learning tool for you down the road or throughout your entire welding career. Welding butt joints. Butt joint welds are commonly made with an oxy-fuel gas torch. Pieces should be clean and flat. And edges should be straight. After the metal is prepared, light the torch and adjust it to a neutral flame. Place tack welds every 3 inches or so, just so it stays in place. Bring the torch to the point where the weld is to start, and the travel angle should be a push at 45 degrees, and your work angle should be 0. To start your puddle, yes, it wants to be at 0. Once we get going, then we'll drop it back down to a 45-degree work angle as well. Tack welds, I usually just put 2 on it because of the size of the steel we'll be working with. One on each end. It will help the plates from warping on you, kind of like the heat is going to, with the size, the thickness, it's lighter metal, 1/8 inch. So all that heat, if we don't have them tacked together, you might start out here in welding and they're tight. When you get to the end, they're going to be spread apart because they're going to get wonky on you from all the heat. So we want to have tacks on each end, and maybe sometimes, students like to add some weight so they don't kind of move around on them. Welding butt joints with an open root, keyhole welding, waiting until the keyhole forms at the leading edge of the weld pool before adding the filler metal ensures 100% penetration. If we see this keyhole, we know that the weld is not only on the top side of these two pieces of metal, but it's also welding on the back side. Total joint penetration is what you're looking for. When you're trying to take two pieces and make them one, we want to make sure that weld is completely through both pieces and they're completely fused. That's going to make our strongest, our best welds. So this procedure is often used on thicker sections of metal that haven't been beveled. Again, we're not going to be beveling anything because of the thickness of our metal at 1/8 inch, but we want to make sure eventually as we go down the road and we start welding open root joints that we have both complete penetration and have good welds on both sides of the base metals. Welding lap joints. The joint consists of lapping one piece of steel metal over the one in which it is to be welded. Before welding metal is added, the weld pool must be C-shaped. Concentrate the torch flame on the lower surface, and the welded portion must be as thick as the original metal. To provide thickness, add enough welding rod metal to make it convex, that rounded look to your bead. Lap joints, again, they're not the easiest to do with oxyacetylene welding. Want to probably do them, start out in flat position, not horizontal. Welding outside corner joints. A V-groove weld can be made without beveling the edges. The keyhole method can be practiced on this joint. Enough filler metal should be melted to form a convex bead. And outside corner joints can also be made without a welding rod. All these different positions and joints that we're going over and the book is going over, we'll go over in the shop before we try to attempt to weld them more in depth, and we'll be able to kind of go over things a lot better when we're doing the actual hands-on. So if it's getting kind of confusing while I'm going over these slides, don't worry. We're gonna go over everything in the shop. I know it's kind of, obviously welding is a three-dimensional hands-on process. To try to do this through slides and pictures, it's not the easiest. So if you're getting confused or you're not understanding everything, don't get stressed out. We'll go over everything in the shop. Also for outside corners, when we talked about like our PPE and our equipment, the magnets to fit these up, you put the magnet right down here, those pieces of metal go on it. It kind of holds it in place so you can tack each end and then remove your magnet and then weld across the joint. The outside corner joints, I love to do these welds. They're pretty easy because the edges of the base metals kind of tell you the width of your weld bead, kind of go right across. Flip them over, do the inside, now you have an inside corner. So you get two welds out of each joint. Welding inside corners, the preferred method is to have the two pieces set at a 45-degree angle, flat welding position. The two pieces should be tacked at points along the joint before welding. Again, this is just taking an outside corner joint, flipping it over. Now you have an inside corner. Welding inside corner and T-joints, the second method is to have one piece horizontal and the other piece vertical. When welding this joint, the torch flame is placed close into the corner to produce fusion at the root of the weld. Hold the torch as close as possible without allowing the inner cone of the flame to touch the metal. The big thing too with this is working from the bottom up. I prefer to do that in every process of welding. You might have instructors that have different ideas about it or different ways they do it. Again, like I talked about earlier, there's 100 ways to kind of do this stuff in welding. If the end result ends up, with a positive outcome, then do the way it's most comfortable for you. But I like to work from the bottom up, just like you're building a house. You start with a foundation, you don't start with the roof. Work from your way up. So when you're welding a fillet weld in oxyacetylene welding, I like to focus my heat on the bottom or the bottom base metal piece and then work that flame and puddle up onto the second piece. It works for me. Hopefully it'll work for you, but that's only going to take practice and time in the shop welding. And like I said, you'll just have to find a way which is most comfortable and works for you. Welding inside corner T-joints again, neither piece of the base metal should show any signs of being undercut, which undercut is you're getting too hot, you're digging into the base metal and not adding enough filler metal, you're moving too fast and you're underfilling. Undercut is bad. It's going to make your weld weak. It's going to create a defect. When we go to test, that's usually where your weld is going to crack. When making a T-joint in horizontal position, use a forward incline half moon torch motion like it shows here in the picture. Let's see what it looks like in the book. So yes, here we got our T-joint horizontal weld in our horizontal position. He's kind of using one of these. Like I said, I like to work from the bottom, wash up, bottom, wash up. It just makes, that way I know that I have a good toe welded, fused, penetrated into this bottom piece of base metal, and I'm washing up to this vertical piece metal. Another safety slide, testing a weld for penetration may be done by striking the weldment with a hammer while holding it in a vise. So yes, once we complete a weld and we want to test it, we'll take it down to the end of the shop, put it in a huge vise, take a hammer, start hitting it, and if it bends it over without breaking, without cracking, you got a strong weld. If you start hitting that and the top piece of base metal flies out, or your weld starts to crack in any way, then we know we don't have a strong weld. A metal screen or heavy material barrier should be installed around the vise whenever you're attempting. We'll show you the area. It's also our grinding area. Yeah, they don't have to worry about it flying across the shop while you're walking there. We'll make sure it's as safe as possible. The screen prevents broken pieces from flying. So yeah, like I said, it's a good way, to make sure that your welds are strong enough and that you're making good welds is to have a destructive test. Welding positions, the recognizing welding positions are flat welding, horizontal with a groove, vertical welding, and overhead positions. Obtaining a good bead is more difficult in horizontal, vertical, and overhead. Like I said, if we can get flat and horizontal down, I will be happy with the way this course went. Vertical and overhead, they're just icing on the cake. I mean, it's a lot tougher. And even an experienced welder in oxyacetylene welding, vertical and overhead positions are very tough. A welder's body, head, and hands should be protected with fire-resistant work clothes, a cap, and gauntlet gloves. A welder should wear high-top shoes or leggings. Pockets should be covered and collars buttoned, and cuffless pants should be worn. Backhand welding. Backhand welding requires the torch to be held at a drag angle of 30 to 40 degrees. The flame should point back at the part that has been welded, using a whipping motion to move the flame away from the weld at frequent intervals so the edge of the pool can solidify into the bead. Because you're having so much flame directed on that bead, they're telling you to kind of get that flame off, get that flame back on. When you're pushing, you're preheating as you go, and your puddle is kind of cooling as you come along. I would suggest and stress that you start out, push travel angle, and get good at it. And then once you have experience and you want to try dragging, you're more than welcome. Or if you're having so much difficulty pushing, then the alternative is to try to drag. But I would get pushing down first. It's easier. The weld is just as strong as dragging. The only thing would be you would probably deposit more weld. Your weld's going to be a little bit bigger dragging rather than pushing. But it is more difficult to drag weld, in my opinion, than it is to push. But like I said, if it comes down to it and you're struggling pushing, then we'll go to drag. Or if you've got push travel angle down and you want to try drag welding, you're more than welcome to. Appearance of a good weld should be of consistent width throughout the length and should be straight, be slightly crowned or convex, appear to be fused into the base metal with a blended appearance, have a clean appearance, and have consistent and efficient penetration and fusion. The best advice I can give you about a good weld or how to make a good weld is stay in your puddle with your arc or your flame at all times and hold your sides, hold the width of your sides. If you stay in your puddle, you're going to have constant heat, which is going to give you good penetration. If you hold the width of your sides, your weld bead is going to be straight, flat, and look pretty consistent the whole way through. So stay in your puddle, hold your sides. Appearance of a good weld, the most common problem in a lap joint is the lack of fusion along the toe or the bead. So this would be an example of undercut. See how the base metal is cut into, and also it seems to me like this isn't, obviously he didn't cap the top here. So you want to make sure that you cover both edges of the base metals. Here we just had not enough fill, so this would almost be like an underfill. You want to make sure that you get at least have these edges burnt in and that weld is flat or straight across from the base metals. Handling torches safely, do not put a cold tip into a hot tip tube. Turn torch hand needle valves only with your fingertips, not with a wrench. Be sure non-combustible materials is in the area. Make sure no combustible materials are in the area when the torch is being lighted. Handling torches safely, do not put a cold tip in a hot tip tube. Turn the torch needle valves only with your fingertips, not a wrench. Be sure no combustible material is in the area when the torch is lit. You just want to make sure, like where our stations are, there are booths behind us. If there are no one in those booths welding, take your tool bags or your stuff, your backpack, whatever, and put it in those booths or around those welders, just so when your workstation area, you don't have something where sparks can fall into your bags or your toolboxes or whatever and can start a fire. We want to keep all those fire hazards away from our workstation. Use a striker to light the torch. Backfires are often caused by a dirty tip, overheated tip. That's another one we haven't talked about, overheating the tip. So we want to make sure that we do have some distance between the flame, our torch flame, and the base metals themselves. If we're putting it right down in there, as close as you can get it, that heat's got nowhere to travel. If our travel angle is a little messed up and it's kind of straight up and down, and that heat is reflecting right off our base metals back into our torch tip, it's going to get too hot. You're going to have backfires. It's going to sound like a gun range in there. So we kind of want to make sure we have a little bit of distance and the heat is off the end of our welding tip. And insufficient work pressures, like I said, if debris comes up there and would stop the flow of gas anytime, you're going to have a backfire. Handling torches safety, use only a clean wood or leather surface to clean the end of the wood tip or the end of the welding tip. Be careful when cleaning the tip with the tip cleaner. We don't want to hone out the hole, make it too big, ruin the tip. We want to be careful with those broaches, the welding tip cleaner broaches. A flashback is a burning back of the flame into the tip, torch, hose, or even the regulator. We have flashback arresters, so we shouldn't have a flashback go all the way there. Just anytime we hear a flashback, we want to shut those needle valves off and isolate the flow of gas or stop the flow of gas. Each welding station should be provided with an insulated hook on which to hang the unlit torch. There is on the side of our workstations where you'll see where the torches get hung up after we're done. And finally, our last safety slide, be sure no flammable materials near your welding station. Be careful that the torch is not directed toward a person while it's being lit. We always want to have the torch pointing down inside our workstations. We don't want to say, hey, turn to the student next to us. We want to have it pointed down. Treat it almost like a gun, like gun safety, torch safety is about the same. If a torch backfires, find a trouble and remedy it before continuing to use the torch. If we have a sustained flashback, obviously we'll end up having to change our flashback arresters because they'll be damaged. In the case of a flashback, immediately extinguish the flame and close the cylinders and regulators. Identify and correct the problem before using the outfit again. Always extinguish the torch before allowing it out of your hands. Always extinguish the torch before allowing it out of your hands. All right, that's the end of chapter 13, oxy-fuel gas welding. A lot of information, a lot of figures, a lot of welding, a lot of different positions, a lot of different joints. So like I said, don't let it overwhelm you. Don't get, if you're a little confused, the book does a great job illustrating a lot of the stuff we talked about. Maybe I should have went back and shown a little bit more of the book. But when we get into the shop, we'll go over each individual joint and each individual weld and position. So again, it's tough with doing this online and doing it, like I said, welding is a three-dimensional hands-on process. To try to do this two-dimensionally is a little bit more difficult. So we'll just, we'll cross those bridges when we come to them. When we're in the shop, when you can see it, when you get your hands-on fill. So other than that, that's it for the chapter. Thanks again for clicking on the video PowerPoints for chapter 13 in your modern welding textbook. If you have any questions, you can always email me at dekurtz@hack.edu. And thanks again.